Okay, we're going to talk about special segments in triangles, and we're going to start with the altitude of a triangle. The altitude of a triangle extends from the vertex, and it is perpendicular to the opposite side. And you've probably already seen this with regard to an equilateral triangle when we drew an altitude perpendicular to the other side. That was the height of the triangle. Now, there are 3 altitudes in every triangle. And if I actually draw all 3 of these altitudes, they all meet at the same point. That's called the point of concurrency. So the word concur means to agree, and so these points all agree, or these segments agree at the same point, the point of concurrency. This particular point where the altitudes meet is called the Ortho Center. You probably don't need to know that anywhere, but I just find it interesting that they all have names. So all the altitudes meet at a particular point. Next up, we have the median of a triangle. The median of a triangle extends from the vertex to the midpoint of the opposite side. So I'll draw a triangle here for you. Make it look a little bit different. And I'm just going to kind of eyeball these midpoints. Just kind of guess where they are. So if I draw this line from here to here, and I told you that was a midpoint, that makes that segment a median. And then I'm going to draw the median from another vertex. And if I draw the median from this vertex, there we go again. We have a point of concurrency. This one is called the centroid. I left a blank for it here. The centroid is kind of cool. It's the center of gravity of this triangle. So if you made a triangle out of a solid shape, out of cardboard or out of wood, and you found this centroid, you could actually balance it on the tip of a pen, because that would be the center of gravity where it would balance. So it's kind of a cool spot. Now, something else about the centroid, it is 2/3 of the distance from the vertex to the midpoint. So we're saying if I take this entire length right here of this median, from the median to the centroid is 2/3, which means from the centroid to the midpoint is the other 1/3. So here's what that looks like. If I told you the entire median was 12, then we know it's cut into 2/3 and 1/3. So what we do is we divide by 3, and we give 2 of those parts to this longer segment and 1 of those parts to the shorter segment. So 12 divided by 3 is 4. So 2/3 would actually be 8, and the 1/3 part would be 4. So they add up to 12. Also notice that the segment from the vertex to the centroid is twice as big as from the centroid to the midpoint. So we've got this 2/3, 1/3 relationship. And what you do, let's say I made it 18. You divide by 3, which would be 6. And so the 1/3 is 6, and the 2/3 is twice as much. It's 12. So if they give you some values of the central or the median segments, that's what it looks like. All right, let's talk about the perpendicular bisector. A perpendicular bisector, we've already defined it in previous lessons. It's perpendicular and it goes through the midpoint because it's a bisector. So it's perpendicular and it goes through a midpoint. Now notice on this one doesn't come from a vertex. It's just perpendicular through the midpoint. So again, I'm going to pretend like this is a midpoint, and I'm going to draw a line. I'll use a different color. That's perpendicular. Okay, it's the perpendicular bisector. It doesn't have to go through the vertex. It can. If the perpendicular bisector happens to actually go through the vertex, then you had an isosceles triangle. So here's another one. Let's say that that's the midpoint, and I'm going to draw the perpendicular bisector of that side. And we'll do the same thing here. I'll make that a midpoint. And if I draw, oh, this is not really very accurate there. Close enough, the perpendicular bisector. You'll notice again, there's another point of concurrency. This one is called the Circum Center. And this one's pretty cool because this point is the center of a circle that would touch all of the vertices. So my circle is not very good. If I had a compass, I could do much better. But if you took this point and made this your radius from here to here, made that your radius, you could draw your circumscribed circle. Circumscribe means to draw it around the triangle. So the Circum Center is the center of that circle. Just kind of interesting to know. And then we have another interesting thing about the perpendicular bisectors. Every point on the perpendicular bisector is equidistant from the end points. Equidistant. What that means is this. I pick a random point on this perpendicular bisector and measure to the end points of that segment, and they're equal to each other. I pick another random point on this perpendicular bisector. If I go to those same two endpoints, they're congruent. So it kind of makes an isosceles triangle, every point on this perpendicular bisector. And we'll have opportunity to practice that. Next up, we have an angle bisector. Well, an angle bisector does just what it sounds like, cuts an angle in half. And this time it's going to extend to the opposite side of the triangle. So again, I'll draw a triangle. Now my angle bisector, this is going to be a hard one to eyeball. So we'll say that angle was bisected. And we'll say this angle was bisected. And then we'll bisect this third angle. I could do this much better if I had a compass. I could be more accurate, but we'll just pretend like those angles were bisected. And notice they all intersect at the same point. That's called our point of concurrency. And for an angle bisector, this point is called the in-center, because every point on this angle bisector is the same distance, equidistant, which means the same distance from the two sides of the angle. So if I pick a point here, let's just take a point here, and I measure the distance from here to the opposite side, or to the side of the angle. Notice when I say distance to a line, it's always perpendicular. Well, this distance, there to there, is equal. So every point on this angle bisector has that relationship. So if I pick any point, it's the same distance to each side of the angle. This is called the in-center because if I take this point and make it the center of my circle, and I pick the correct radius, and I'm really bad at drawing this one, I could inscribe, I told you I was bad at this, a circle inside of my triangle. Again, a compass, I could do much better. But this point is the center of the circle that's inside the triangle. And this one, because circum means around, this was the center of the circle that's outside of the triangle. You don't have to do that, but it's interesting to know. So let's kind of practice a couple of these little rules we learned and see what we can do with them. So this one says BD is the perpendicular bisector of AC. So I'm going to label that. It's perpendicular and it's a bisector. So BD is the perpendicular bisector of AC. Well, one of the things that meant with our perpendicular bisector is every point is equidistant from the end points. So that means point D is the same distance to C as it is to A. So that's an easy one. I'm just going to say 3x plus 14 equals 5x. Solve for x and then I can answer the question. So subtract my 3x, I get x equals 7. So now I go back and check it. 5 times 7 is 35. Let's see if I did this correctly. 21 plus 14 is 35. So they wanted to know the distance from A to D, and we found that it was 35. Because this was a perpendicular bisector, created an isosceles triangle. Now this one, if you notice, right here, this is an angle bisector because 27 and 27 are the same. So that means these distances are the same. The distance from a point perpendicular to the side of the angle. So all I have to do here is say 6x minus 5 equals 5x. Subtract the 5x, add the 5, and we have found the value of x, just like it asked. All right, the last one has to do with a centroid. So if they tell you that D is the centroid of the triangle, we know the centroid comes from where all of the medians intersect. And remember, median means midpoint. So if D is the centroid, that should say G. Sorry about that. G is the centroid. And I tell you that BG is 6. AF is 12. And AE is 15. And now they're going to ask us to find some other pieces. All right. So let's start with FC. Well, remember, medians have to do with midpoints. So if F is the midpoint, AF is 12, guess what FC equals? Well, it must be 12. The next question has to do with BF. So here's BF. So remember, we told you that if this is a median, I'll just draw it. It's split into two pieces. There's a 2/3 and a 1/3. So this one is 6. So 6 is the 2/3. So if I divide by 3, 6 divided by 3 is 2. I'm sorry, 6 divided by 2 because it's the 2/3. So basically think of this one as 3 plus 3. And then you can realize that this one down here is the other 3. 6 gets 2 of the 3's, the 1/3 gets the other 3. That makes BF altogether equal to 9. If that didn't make sense, you could always say that we know that BF, 2/3 of BF is BG. So if you wanted to say that 2/3 of this is 6, then you could come over here and find out that if I multiply both sides by 3/2, I get 18/2, which is 9. So it works that way. Let me do this one more time. If 6 is the 2/3 part, divide it by 2 and get 3 plus 3, which means the 1/3 part is one of those 3's. So here's our thirds. 1/3, 1/3, 1/3. 6 got 2 of them because it was the 2/3 piece. All right, let's talk about AG. Notice that AE altogether is 15. So remember, we're splitting it into the 2/3, 1/3 piece again. So this whole thing is 15. So divide it by 3. 15 divided by 3 is 5. So this gets a 5, and the 2/3 gets a 5 plus 5 because there's 2 of them. So A to G is 10, and G to E is 5. That's the 2/3, 1/3. All right. One last thing, just to refresh your memories, because part of the title here is special triangles as well. We have worked on 45, 45, 90s, but they're going to come up again. So just to refresh. So if I took this triangle, let's say it's ABC. Be real creative here. If A is 7√2, what would that make B and C? Well, remember our rules. We had the leg is X. The other leg would also be X, because remember, if the angles are the same, the sides are the same. And the hypotenuse for a 45, 45, 90 was X times √2. So now I take my leg that they gave me. If A is 7√2, well, B is the same thing. And then the hypotenuse is this leg times the square root of 2. So 7 times the square root of 2 times the square root of 2 is 14. And then what if I told you that the hypotenuse was 15√2? This is where it gets easy. What does that make the two legs? Well, if the hypotenuse is X times the square root of 2, then X is 15. And those are my two legs. Just a quick refresher. Let's take our 30, 60, 90 real quick. Here's 30. That's across from, let's call it M. And here's my 60, N, and we'll call that one P. So we've got short leg, long leg, and hypotenuse. So if I tell you that the short leg is 5, you should be able to tell me that the long leg is 5√3 and the hypotenuse is 10. If you need to look at your formula sheet for that, that is okay. Now, what if I told you that the hypotenuse was 8√3 and asked you to tell me the short leg and the long leg? Well, we look at our formula. The hypotenuse is 2x, the short leg is x. So how do I get from here to here? I divide by 2. What's 8√3 divided by 2? Well, it's 4√3. And then once I know the short leg, because remember this was home base, we always went to the short leg. Once I know the short leg, how do I get to the long leg? Well, I take this one times √3. Since √3 times √3 is 3, the long leg is actually 12. So just a quick refresher, you're going to have some more practice on that, as well as your trigonometry, your sine, cosine, and tangent.